Hey there, curious minds. Ever tried to picture what a quantum computer actually does? It's like trying to watch a symphony played by invisible instruments, abstract, complex, and full of hidden patterns. But what if we could see the math behind it all? That's where visualization tools come in, and they're turning quantum computing from a mystery into a playground. Let's start with the basics. Quantum computers use qubits instead of classical bits. Unlike a normal bit, which is strictly 0 or 1, a qubit exists in a superposition of both states simultaneously. Think of it as a spinning coin that's neither heads nor tails until it lands. This property allows quantum systems to process information in parallel, solving certain problems exponentially faster than classical computers. But here's the catch. Understanding how these systems work is like trying to read a book written in a language you've never seen. The math is dense, the states are non-intuitive, and the interactions between qubits defy classical logic. That's where this new tool shines. Imagine a digital lab where you can tweak parameters, watch quantum gates, the building blocks of quantum circuits, manipulate qubit states, and see how a quantum system learns from data. It's the TensorFlow Playground of the quantum world, interactive, intuitive, and full of surprises. Whether you're a student, researcher, or just a tech enthusiast, this tool demystifies the quantum realm by turning abstract concepts into visual experiments. Now, how do you even visualize something as weird as a qubit? Enter the Bloch Sphere, a 3D representation that maps quantum states onto a unit sphere. The north and south poles correspond to the 0 and 1 states, while the angles theta, polar angle, and letter 3d5, azimuthal angle, define the qubit's superposition. Think of theta as the tilt of the qubit and letter 3d5 as its phase, like the rotation of a spinning top. This tool is invaluable for single qubit systems, but when you add entanglement, things get more complex. That's where the Q-Simplex comes in. Picture a tetrahedron where each vertex represents a possible state of 2 entangled qubits, 0, 0, 0, 1, 10, and 11. The edges and faces highlight entangled states, like the famous Bell states, which are maximally entangled. While the Q-Simplex sacrifices some phase details, it uses color gradients and size variations to hint at these properties. It's a clean, geometric way to explore multi-qubit interactions, though scaling this approach to larger systems remains a challenge. Here's where it gets really cool. The tool lets you watch a quantum classifier learn. Think of it as a quantum black box that adjusts its parameters to improve performance on tasks, like recognizing patterns in data. You can drag sliders, flip switches, and instantly see how tiny changes ripple through the system. It's like watching a recipe evolve in real time, except the ingredients are quantum states, and the dish is a machine learning model. For example, you might tweak a gate's angle and watch the system's accuracy jump, revealing how quantum circuits optimize themselves. Of course, this is just the beginning. Scaling up to more qubits is a huge challenge. Current visualizations work well for 1 or 2 qubits, but entanglement in larger systems is still a mystery. Researchers are exploring new frameworks, like tensor networks and quantum tomography, to map these complex states. The goal? To make quantum computing not just powerful, but understandable. So next time you hear about quantum breakthroughs, remember, behind the headlines are tools that turn abstract math into visual stories. And that's what makes this field so exciting, because if we can see the quantum world, we're one step closer to mastering it. Thanks for watching. If you want to dive deeper, check the description for links to the tools we discussed. And if you're hungry for more, hit subscribe, because the future of AI and quantum computing is being built right now, and you don't want to miss the ride. Stay curious.